Thanks for joining me. Welcome, everybody. Today we're going to be talking about organic compound nomenclature. Organic compounds are primarily composed of the atoms carbon, with the symbol C, and hydrogen, with the symbol H. But they may contain additional elements such as halogens, oxygen, or nitrogen. What makes carbon such a prolific element is that it can bond with up to 4 of its neighboring elements. One thing we need to keep in mind when representing electrons in atoms is that electrons in the valence shell of an element must hybridize to form a chemical bond. There are usually 4 bonding orbitals. When we see a non-bonding pair of electrons, no bonds will form. But when we see a lone electron, we understand that as being a site where one bond can occur. The element carbon has 4 valence electrons. We know this by looking at its group number on the periodic table. In this case, Roman numeral 4a gives us 4 valence electrons. Notice how carbon has 4 lone electrons. This equates to the 4 bonds that carbon must form. No more, no less. When we look at the electron structure of hydrogen, we note it has a single lone electron and no non-bonding pairs. It will form 1 bond. Classes of straight-chain carbon compounds, alkanes. When naming hydrocarbons, the starting point is naming straight-chain alkanes. Alkanes follow the formula CxH2x plus 2, where x represents the number of carbon atoms. Hydrogen will always have twice as many atoms as carbon, plus 2. Let's draw CH4, also known as methane. What we see here is that the lone electron on the carbon and the lone electron on the hydrogen overlap to form what is called a shared pair. We can think of it as a chemical bond. The red electron associated with hydrogen is attracted both to hydrogen's nucleus and carbon's nucleus due to an opening in carbon's valence shell. The black electron on the carbon is attracted to both its nucleus and the nucleus of the hydrogen. Together they form a chemical bond. Here we show the methane molecule in its final form. We've replaced the dots with lines. Let's look at C2H6. It follows the correct pattern of an alkane, twice as many plus 2 hydrogens relative to carbon. Note how we've identified that the carbon-carbon bond reduces the total number of carbon-hydrogen bonds that can be present. Each carbon forms 3 carbon-hydrogen bonds and 1 carbon-carbon bond. Always check your work. Every carbon should have 4 chemical bonds, no more, no less. Every hydrogen should have 1 chemical bond, no more, no less. Always review your work before you proceed. Now I want you to try and draw C3H8 propane on your own. An alkene is a straight-chain alkane that includes 1 double bond between carbon atoms. All alkenes follow the general formula CxH2x, where x is the number of carbon atoms, the number of hydrogen atoms will be twice as many as that number. Exactly. So here you see me circling 2 pairs of lone electrons to demonstrate where the 2 bonds are going to form between the carbon atoms. That leaves 2 remaining lone electrons around each carbon. Let's represent this another way. Notice how I've oriented the electrons around the molecule. Recall that electrons are all negatively charged and as such will repel one another. We've drawn it this way so that every electron pair around the carbon atom is equidistant from every other electron pair at roughly 120 degree angles. With C3H6, we've included a double bond between the first two carbons. If we had put it between the second and third carbons, it would be the exact same molecule, just rotated 180 degrees. Classes of straight-chain carbon compounds, alkynes. An alkyne is a straight-chain alkane that includes one triple bond between carbon atoms. Alkynes always follow the formula CxH2x subtract 2. So for every carbon, there will be twice as many hydrogens, less 2. Let's draw an example. Notice how the 3 chemical bonds between each carbon leaves one bond remaining on each carbon, hence the formula and structure we see. With our second example, we need to put the triple bond in one of those two positions. Now, wherever we put it, it'll end up being the same molecule. If you put it the first bond or the second bond, they'll represent the same molecule rotated 180 degrees. The outer carbon that is attached to the triple bond can accommodate one additional bond. The carbon in the center has 4 bonds and can accommodate no additional bonds. Naming straight-chain carbon compounds. There are 2 parts to naming a straight-chain carbon compound: the prefix, which tells us how many carbons, and the suffix, which tells us how many hydrogens. Here's a few quick updates for the prefixes. In our example, propane, the prefix pro tells us there are 3 carbons. By inserting 3 as X, we can solve for the formula of propane, C3H8. Try these practice problems. Let's do the first one together. In the case of propene, we identify the prefix prop as telling us that the compound contains 3 carbon atoms. The suffix -ene gives us the information that we'll have exactly twice as many hydrogens as carbons. When we write our formula, we replace the X with the number 3 and solve. Naming compounds. Some compounds can have double or triple bonds in different positions. We number each bond in the compound and include a number before the name to denote the location of the double bond. In this example of 1-butene and 2-butene, note how the double bond indicated by the suffix -ene is in the 1 position. In this next example, notice how the double bond indicated by the suffix -ene, E-N-E, is in the 2 position. Notice how we put the hydrogens on opposite sides of the chain. This is because we're trying to accommodate the repulsion of electrons. They want to be as far apart as possible. The question becomes, why no 3-butene? Well, let's draw out 3-butene and compare it to 1-butene. Notice how a double bond in position 1 or position 3 represent the same molecule rotated 180 degrees. This is why when we count the bonds in a chemical compound, we count from left to right or from right to left. Whichever direction gives us the smallest numbers in our name. So isomers, as we have just discussed, are when 2 compounds have the same formula but different chemical structures. An example of this might be 2 compounds with the same formula but very different boiling points or flash points. A flash point being at what temperature it becomes an explosive. You can see how in industry or on the workplace, this is very important information and we must discriminate between the 2. A famous example of an isomer is the drug thalidomide, which was used in the 1950s and 60s as a treatment for morning sickness. Now, the one isomer of that compound had our mothers that were feeling sick during their pregnancy would get rid of their morning sickness. But The problem then came is if you got the other isomer, it caused your child to be born without arms or legs. In this case, the study of isomers and the distinction between molecules that have the same formula but different structures becomes ever so critical. Here we're looking to name the following compounds. Let's do the first one together, and then I'll draw 3 for you to name on your own. When naming a compound, we need to assign a prefix that corresponds to the number of carbons. In this case, the number is 2. The prefix we're going to use is the prefix F. There are exactly twice as many hydrogens as carbons. This relationship between carbon and hydrogen indicates that it is an alkene and will end in the ene suffix. We put them together and we get the name ethene. Now make sure that you attempted all of the practice problems indicated in this video on your work when you submit it. Thanks for watching. Good luck, everybody, and take care.